In the last video, we looked at some few definition of terms, that was a random experiment, a sample space, a stochastic process, and a state space. Today, we are going to look at some useful stochastic processes. Here we describe several different types of stochastic processes which are useful in setting up a model in time series. The first one is a pure random process, or what we call a white noise. We say that a discrete stochastic process is called a white noise if it consists of a sequence of random variables et which are mutually independent and identically distributed with a mean mu and variance sigma squared. We say that it is a process without memory, or simply it is memoryless. That is, the value of the process at time t is uncorrelated with all the past values up to time t. Hence, it cannot be used for forecasting. The next useful stochastic process is what we call the random walk. For a random walk, we define it as follows. Now, suppose that ET is a discrete purely random process. Remember, a discrete purely random process is a white noise. So, we suppose that ET is a white noise with mean mu and variance sigma squared. A process xt is said to be a random walk if xt is equal to, that is, xt is equals to xt into t minus 1 plus epsilon t, and we can say that x naught is equals to 0. Thus, if we substitute our xt, let's replace xt with x1, so x1 will be given by t1 minus 1, that is x naught, plus epsilon 1. But remember, we said that x naught is equals to 0, so we can replace this term with 0. So simply x1 is equals to epsilon 1. x2 again is equals to x2 minus 1, that is 1 plus epsilon 2. Therefore, and we said that x1 is equals to epsilon 1, so we can replace this term with epsilon 1. So xt is equals to epsilon 1 plus epsilon 2, and the process continues like that, making those substitution. Hence, we can conclude that xt, our random walk, is equals to xt minus 1 plus epsilon 2 is the same as epsilon 1 plus epsilon 2 plus epsilon 3 all the way to epsilon t. Therefore, in simple terms, we can write it at xt is equals to the summation I is running from 1 to t of epsilon I. We can also look at expectation of this process, the mean. Therefore, we can say that expectation of xt, simply introducing expectation in this first term here. So expectation of xt is equals to expectation of the summation of I running from 1 to t, summation of I, which is equals to, we introduce expectation inside here. So, but we know expectation of epsilon I is equals to mu, but we are summing t times, so mu times t. The same case for variance. The variance of xt is equal to the variance of the summation of epsilon I running from 1 to t. This is equal to the summation of, now the variance goes inside, variance of ai. But remember, we see that ai is normally distributed with a mean of mu and variance sigma squared. So the variance of epsilon I is sigma squared, but how many you are summing t times, so t sigma squared. Actually, the process is non-stationary. Why? We can see it is depending on t. Hence, the process is non-stationary. However, we note that the first difference, this is the difference in now here, the first difference, that is xt minus 1, we get epsilon t, which is actually a white noise, which is a purely random process, or rather a white noise, and it is stationary. So we can say that a random walk is an unstationary process. However, difference in it, the first time they will be stationary.